And then close the door. He said like last call. I was like, then close the doors. Okay. Okay. Hello, everyone. So we will talk about Magnetron, more about Magnetron. Dr. Ayub has already covered a lot of these concepts. I will.
Can you close the microphone?
Goodbye.
I think it's better.
It's closer. I mean, like I feel it's hiding. Like it's not coming up. Can you guys hear me in the back?
Yes.
Okay, better. Okay. So a lot of these concepts will be repeated somehow, but it doesn't hurt if you hear the same information twice. Probably will remember it for longer time. So here you do this. Here's the our experiment, one of the experiments at UNM. So I think I showed this the first week. I'm just trying to show you like the high power microwave devices are bulky, huge, and it needs a lot of careful designing and machining in order to have then the correct experiment. And if you do anything, if you have a mistaken design, really hard to fix it when you have everything built. So that's why Mohammed was telling you like volume, you change the volume, you change the frequency. It's easy in simulation and theory, but once you have that thing machined, it's gonna be a challenge how to change the frequency, how to tune it. Everything is gonna add to the problem. Now, the two main magnetron that we have at UNM, they are not, of course, we talked yesterday about explosive electron emission. It's really very high voltage, high current devices. And those are called A6 magnetron because they have 6 cavities. And if you see here, and we call them MRO magnetron with radial output. Means like we're gonna extract from one cavity or more. And MDO is magnetron with diffraction output, basically with axial extraction of the RF. When we say extraction, is the RF extraction, microwave extraction. So these are the two schemes that we follow. Every single one has advantage and disadvantage, but Thor, the device or the machine I showed you the first day is based on the MDO, and this is the real MDO at UNM. So A6 magnetron was invented by McAfee in 80s. People before that, they knew magnetron. They have done conventional microwave devices using thermonic emission. But in the 70s, I think, they came up with the pulse power. So just to let you know, conventional devices that can generate kilowatts of power, they use power supplies, modulators to drive them. And those are basically, can go high voltage, but the currents are not in range of kiloamps. A pulse power like Marcus generator can produce currents of kiloamps. And that allows you to generate a gigawatt of power, but at very short pulses. Now, you saw this picture. It's basically comes from yesterday. idea that you have Faraday-Landmeyer law in the coaxial symmetry, and this is the diode basically. When you apply voltage between the inner and outer electrodes, electrons will start, born here on the surface. But you need to have some insulation because you don't want to just lose the electrons with the conduction. And this is because the whole switch was invented as a magnetic switch, basically. If you have too much magnetic field, you have off, switch is open. If you have no magnetic field or reduced, you will have conduction, and you're gonna have your switch on or connecting. Now you have to have some value in between, and of course these electrons, they don't just follow just straight trajectories. So they have some curvature and cyclotron behavior. So I'm not gonna talk about this in more details, but this equation is the whole cutoff. Is basically what I wanted you to know is this approximation that the two knobs that you have when you design your magnetron to play with is the magnetic field, which is basically either permanent magnet. If you have a permanent magnet, you don't have a knob actually, but you can you can add maybe some coils to the your machine. But if you have coils, basically Helmholtz coils, which is basically some set of coils, two coils, they have the radius and the distance between them are equal. So some arrangement to have a flat magnetic field on axis of your magnetron. And by having this setup, now you have one knob, and second knob is basically changing the voltage, applied voltage between cathode and anode. If you have those two, you can select your operating point and you select your mode. Okay, there is, a lot to describe or like to discuss in this context, but there is basically a lot of, space of parameter that you can choose from, but you can't have any combination of voltage and magnetic field because you could be in the cutoff region, and this is below Bowman-Hartree threshold, or you could be in the conducting, which is basically above the whole cutoff. So you need to be in this region here, and this curve is not fixed for all modes, for all magnetron. Depends on the geometry. It depends on the mode. This could be like a very small, space of solution. Yeah. Do you have a question? Are we good? Okay. So, kind of a lot of this information you already heard this morning, but for all the slow wave devices, dispersion engineering, dispersion characteristic relation is the key. This is your starting point, how to design or even analyze if you have some device that you need. So I will discuss this in more details in the afternoon session. I will kind of carry you from the basic waveguide parallel plate setup and go ahead and have, once you have corrugations. And yesterday I showed you maybe, if you have two plates, this is parallel plate, but if you have one of them have some corrugations, I made this one. So these are corrugations of the surface, basically cavities. In magnetron, they really have a more depth than what you see here. But if you twist this around the cathode, this is the cavity, right? You see? And if you have this, I can twist it in other coordinate, but if you have this twisted in this coordinate, basically, you're gonna have a linear devices like a BWO or traveling wave tube. So you can treat both problems in a parallel plate setup with the one of the plates are corrugated, and this is what I'm gonna show you afternoon. And this is basically the first step to design your source, to get the dispersion curve and to understand it very well. And then using this dispersion curve, you can choose what mode of operation, pi mode, 2-pi mode, or something in between. What's the meaning of pi mode? You have heard about this. It's basically the phase shift of the electric field between cavity and adjacent cavity. Are they like having pi phase shift? Means like they are opposite to each other, 180, or 2 pi, they are in the same direction. Those are in the dispersion curve is very obvious here. This is dispersion curve for A6 magnetron 6 cavities, and this is the field distribution. The field, this is like cold dispersion curve. Means there's no electrons here. Once you introduce electrons, you're going to end up with a coupled dispersion curve. Everything will be distorted. And it's very hard to follow. But you know, you need to start with a cold structure for your design. And once you introduce the electron beam loading will introduce, you know, other physics to the problem and change the frequency slightly. But for any case, so this is the dispersion curve for the first pass band. We call pass band means this band here, these frequencies are possible to be generated. But the frequency from here all the way here, they are stop band. Stop band means you can't generate them. It's cut off. Remember from the waveguide concept, you have, I will explain this maybe in simple terms afternoon. If you have a waveguide, you have a lower cutoff. But if you have a slow wave structure, you have more boundaries. Then you have lower cutoff and upper cutoff. Not only, so you're going to have a kind of a filter behavior. Pass band, stop bands, pass band, stop bands. And now what you see here, this is the 2 pi mode and pi mode, and there is like a couple of other modes that can exist. And usually in the call test, when we do call tests, either by computer simulation or in the lab, yeah, you're gonna end up with points, and these are resonances basically. And these points depends on the number of cavities. For azimuthal or circular devices like this, magnetron, CFAs, you will have n over 2 plus 1 resonances, n number of cavities. If you have 6 cavities, you're going to have 4 resonances. So 6 over 2 and then plus 1. If you have more cavities, you're going to have different number of resonances. For linear devices, when you twist your slow wave structure in other direction, basically, you will have n plus 1 number of resonances when you do the call test experiment or you do your homework in 3D electromagnetic software.
May I ask you a question?
Yeah, go ahead.
So, what is the dashed line? Is this velocity of?
This one?
Is the dispersion diagram of velocity? Is the dispersion diagram of light?
This one most likely is the beam. Is the beam dispersion line?
Yeah, beam dispersion line.
Yeah,
okay.
It's electrons. Okay. Yeah. So this is like simple way of thinking about it. But once you have electron beam, I will show that dispersion curve will be distorted, will be changed because you're going to add instabilities. And this is how we extract RF from electron beam. You know, at the beginning, first couple of nanoseconds, the electrons are going in a uniform velocity. So there is no modulation actually, right? And then after like a couple of nanoseconds, you start having some modulation, bunching, and you saw the spokes this morning, right? Spokes like depends on the mode. Number of spokes here are different than number of spokes here. We will talk about.
If you look at this figure, can we say any operation of bandwidth about this structure?
Yes. Yeah, we can tell the frequency of the operation.
Yes.
And this is
a bandwidth.
Hmm?
Is this point or a bandwidth?
No, it's very high resonant cavities, so that's like very small bandwidth.
Small line.
Yeah, we just talk about one frequency, but plus minus because it's high Q structure.
Yeah.
Yes. I will show when we have MDO, we open the all cavities, we start having less Q and start, suffering from some other problems, right? So it's all, trade-off. Like you can have improve this and lose that, so it's always like there is no optimum solution for all cases. You saw this, the equivalent of resonant circuit. There is no resonant actually lamped element, but like we just approximate cavities as RLC circuit, and this is just to understand, and you can calculate or approximate what operating frequency. But this is like very, very rough approximations, not accurate. I think I showed this, but this is basically as you go up in frequency, your structure will be smaller and smaller. So the problem is, you are limited with the power. Your breakdown is going to be limiting your operation. This is the electron spokes. You saw electron spokes this morning. For A6 magnetron, you see 6 cavities, means if the field between cavity to cavity are 180 degrees, which is pi mode, you're going to have 3 spokes. And the spokes, they are not starting from the, once you apply the voltage. The pulse that you have probably 15 nanosecond, first like 10 nanosecond, you have no generation, still like, a lot of mode competing. There is no mode formation. But after a couple of seconds, nanoseconds, you end up with the defined spokes. But this is from Magic software. And this is iSpec, which is a software that's not available to everyone. But you can see this is more accurate, pick code because of the feedback. All of these devices based on plasma science, and there is a lot of approximation. If you don't have an experiment, gives you feedback to adjust, tweak some fudge factor in your software will give you just, nonsense results. Yeah.
Spoke formation, does it depend on the mode?
Yes.
Every mode has a different spoke configuration.
Yes. So this specific mode, this is we call pi mode because we take a look at the electron, but this is basically introduced TE31 mode in circular waveguide. Yeah, 3 spokes. If you have 6 spokes, you can have TE61, mode. And these are all modes, like they have hotspots. You need to change them. So one of the reasons they pick pi mode is stable, and also it's easier to change it to fundamental mode. I will show mode conversion, how to transform the mode to radiate. Like always, we want to have a laser beam type of beam of electromagnetic. So to use it, right? It's easier to use. Now, this one is not very obvious, but it shows you this is 2 pi mode. 2 pi mode means the phase shift from cavity to cavity is 2 pi, which is 0 phase shift, right? There is no phase shift. So this is the cross section, just to give you like a perspective. This is what you see here. What you see here is this cross section. What you see next to it, this one, is this cross section, basically. So that's why you see this is the vein. We call this vein. These are veins. These are the conductive material. This is vacuum. So these cavities have vacuum. And this is not so clear, but it shows like somehow the field, electric field direction. And this is RF field. It's all very confusing when you start this field, this electromagnetic or like high power microwave. You will see people like talk about beam, field, and this could mean anything. If you take like antenna class, they tell you the radiation pattern beam. But when you come here, you say an electron beam, things changing, and there is like electromagnetic wave propagation. There is a radiation pattern beam, but still like you need to be, you need to understand, to learn the language basically before you do you jump in this field and understand everything. Also, when you apply the pulse between these electrodes, cathode and anode, you will introduce electric field, which is static kind of because it's a pulse. And after E cross B drift, we talked about E cross B drift velocity, right, yesterday. And this is what causes the electron from the beginning to start like doing this E cross B drift transfer. And then after a while, the electromagnetic from noise, yesterday, I think I heard someone has a question, how we can get, I think online section, how can we get RF with no input signal. So these oscillators start from noise. We start from noise because of the dimension, because of the, this maybe explosive emission in this case. You will start one frequency and you grow this frequency from white noise. For the amplifier, you start from seed signal, of course. So your electromagnetic RF will have also E cross B drift. And this is what causes these spokes to form. So this is like in the kind of a lower layer of the description. Okay, now this is 2 pi mode for 6 cavities. Now, again, I was talking to you about the whole cutoff and the bone marrow artery threshold. This will change from mode to mode, from structure to structure. You look at this one for A6 magnetron, for 2 pi mode, your ranges of operation is really small here. If you are talking about around 400 kilovolt. Always the 2 pi mode has higher frequency. Maybe I can go back to the dispersion curve. This dispersion curve. This is 2 pi mode or 0 mode. Usually it has a higher frequency than pi mode because it's next passband, higher passband. Okay. Now, if you generate the RF, how can you extract the RF out of the cavity? You can have one cavity, and this is the usual way, radial extraction, we call it, radially. And this is what you see here. You're going to have a radial extraction. You're going to have a window and radiate. And maybe Bakafi has these different schemes. And in the morning, Muhammad showed you this one. It's basically extracted from 1, 2 cavities, or maybe all cavities. But this is going to reduce your Q factor. And with reducing Q factor, you're going to lose resonance between the electrons and the electromagnetic wave. And it's not always a good thing to do. This one is opening from the axial direction. As now back to our nice sample. If you have a radial extraction, you're going to have your waveguide comes from here. If you have a diffraction output, the RF comes out of this side. Now, this is the basic principle of MDO. Again, there's different variation. So extraction of the RF is not related to the operating mode, right? Because like you can have any operating mode and you can extract the power. It's not related. But the reason why people want to do radial extraction, because in this is the cathode, this is the side view, right? And now we're generating electrons around here, and they are start circulating. But in the same time, I showed you yesterday, is not only circulating in position, they are like trying to go in the axial direction. They are leaking. We call it leakage current. Leakage current is reducing your efficiency. Basically, you're losing electrons without extracting the energy out of them. And to stop this, they put like end caps, reflectors. There's too many ways to trap these electrons and extract more energy out of it.
End caps on the cathode?
Yes. That's on the cathode. Now this curve is this figure shows the power and number of cavity, if you open number of cavities, and this is the total power. The total power, if you open 1, 2, 3 cavities, increases, but if you open more cavities, decreases because you're losing resonance, basically. You're not interacting efficiently with the electron field. This is a view, again, if you have radial extraction, you kind of like you're safe from losing electrons and hitting the window, because if you have axial extraction, this one here, if the electrons leaves here, they're gonna fly and hit the vacuum window. Vacuum window is basically plastic. This is where you have vacuum here and you have air here. And you need to have a vacuum window. And if you have high energy electrons hitting the window, you break the vacuum, you might crack it and you're gonna lose the vacuum. So for radial extraction, you're safe from this, but for axial extraction, need to be, doing more of the end cap, and the end cap cannot be very close to here, because if you have a big end cap here, you're gonna have small opening, you're gonna end up with arcing. And this is problem. And if you move your end cap away here, the magnetic field that guides electrons will go like in this direction. So even if I have a big end cap here, is not going to trap any electrons. So you need to have your end cap closer to the interaction region, but not big. That's going to block the, going to cause static. Yeah, this is one of the nice animation that shows the 10 cavity magnetron, and these are the number of spokes. Can you tell me like what mode is this? How many spokes do you see?
5.
5, right? And
5.
how many cavities? 10. So basically pi mode. If you have half number of spokes of the cavity is pi mode. If you have same number, is going to be 2 pi mode. In between, you're going to have some other combination. And how many resonance points, if you want to test this in fault test, how many resonance points you're going to end up having with the 10 cavities? 6, yeah. So 10 over 2 plus 1, right? So 6 points you're going to end up with for that. So for the 8 cavities, this is again 4 spokes, which is for the pi mode. And of course, this is because of the stable deformation. Yeah, this is very nice, showing the direction of the electric field, RF electric field. So it is 180 degrees from cavity to cavity. Again here, this is 180 degrees. So more about extraction here. I don't think this is adding any more information. So the axial extraction MDO was done in Russia in the 80s, but they abandoned it because they got very low efficiency at the beginning. Fuchs, he was my co-advisor. He did the experiment in Russia in the 80s, but it didn't produce any significant improvement on radial extraction, and then they abandoned. In 2000s, a group in Japan, they revisited the problem, and they found that the Russian were having a waveguide cutoff dimension. So they are not radiating the generated power, they are trapping it. So when they changed the dimension and they allowed the mode to propagate, they got, I think, 35%. And then Fuchs in 2005, he saw the paper, and then he went back, ran some magic simulation. He increased the efficiency to 70% at UNM. And how to increase? By changing the flare angle of this. So these are the veins, and the veins kind of continue with the flare angle, smoothly extracting the power. And he was able to get 70% with what we call transparent cathode. And this is, another advantage was added at UNM, another contribution. Most of magnetron use solid cathode, just electrode. But let me, this is again more study for the MGO at UNM. And this is the MGO. So how to machine this back, I think in 2012, I think 13, they machined this. I think the cost was maybe 29K or something. Now it costs 75K to machine this. And it's very difficult because the problem is like you have a bigger structure and you don't want to have any variation in your cavities. You have to have them all symmetric. If you have any variation, you're gonna have a mode competition and you're gonna lose the efficiency. Yeah.
What are the dimensions?
So I have the numbers, but the whole structure is like this big. This one, what you see, so it's basically less than, I would say, like maybe 70 centimeter length, and this is 50 centimeter radius. Yeah.
These vanes are individually machined or from?
They are individual machine, and then they weld them. There is like a whole process, and they have they build a structure that to be in place during the whole process.
Yeah.
So to keep everything in place, alignment. Yes, it's really very nice. These are some steps, but I think there is more steps to how to assemble these vanes. I think I was trying to talk about transparent cathode, but let's move it back a little bit. Here is the some sort of the MDO. So basically A6 magnetron is this piece right here. All of this whole thing is the transition to extract the power, basically. So this is the difficulties. Now, when they tested this at UNM, they have a lot of power here, and they start having a breakdown. And I think I mentioned this. You have to add some, SF6 in the front of the window to avoid having breakdown. But since this is a pi mode, so the phase shift between cavity to cavity is pi. If you block two cavities, we are not blocking complete cavities. The end of the cavity, we block them. So we have a plate here. We just plug this and allow the rest to radiate. We end up with radiating TE11 Gaussian beam. So this is very simple mode conversion, mode transformation. It's very, very, very nice, and needs to do like a lot of optimization, because when I talk about transparent cathode, you will see how things you have to align different things. Here we go. So before doing the research for the MDO, UNM was involved in how to improve the performance of the relativistic magnetron. And one of the problems is that magnetron starting so late, start the oscillation. So if you have a pulse, maybe 20 nanosecond pulse, you're probably not generating RF, because still mode formation takes time. BIVO, backward wave oscillators, that I will discuss afternoon, they have very fast start of oscillation. The feedback is very efficient, but magnetron, it takes time. So one of the problems that is, how can we have relativistic magnetron operating with the very short pulses? And they came up with the transparent cathode. Transparent cathode is basically similar to solid cathode. You have to have like emitters instead of, and we are not emitting, actually, we are getting the electrons from this side. Okay, so the electrons will be circulating here and forming spokes. In fact, these emitters will enhance the spokes as well. They call it transparent cathode because the field can penetrate here to the axis. So the field on the surface of these emitters is not zero, because you have tangential component of the electric field will be forced to be zero on the surface, right? But this one, you will have higher fields, so that the electrons born on these emitters will have a favored phase. They already synchronized, so they have a faster starting time. So they, UNM, they were able to run this, on CNS machine. Let me go back here. On CNS machine, which is 16 nanosecond pulse, and we were able to get, RF, even though the pulse is very short. If you have a solid cathode, the generation is not going to start. So this is the comparison between solid cathode. There's another, Michigan, they have another idea of priming. It didn't work in experiment at all, but their simulation shows some promising, but still transparent cathode worked. Look here, at the same time, transparent cathode start forming the spokes in at the early time, and at 5 nano or 6 nanosecond, you have all the spokes formed, but the solid cathode is still trying to start depunching. Yeah.
What sort of priming we're talking about?
What sort of
Priming.
priming? Oh, they did like, I think, magnetic priming. Yes, but I think in experiment they were not getting any results. So it was good on paper only.
They only tried one magnetic priming.
Yes. Yes. And they have like, there's a lot of publication about their work. YY and other group like they have. Okay, so for this, this is A6 magnetron with radial output. So they tested with the transparent cathode, and they were able to not only improve the starting, also they improved the power generation and clean FFT kind of. This is the FFT, the frequency of generation. And also the microwave, this is comparison between microwave for, I think, solid and transparent cathode. So the power is higher with the changing the magnetic field. Sorry. Also, when they did the experiment for MDO, they were able to increase the efficiency by introducing the transparent cathode. Remember, like when first experiment for MDO in Russia, this experiment, they were using solid cathode, and the group in Japan, they used solid cathode, but they got 35%. When UNM introduced a transparent cathode, they were getting maybe 60% efficiency because, you know, the transparent cathode has this advantage of electrons born in favor phase. Again, Fuchs did this, you know, this project, as Ayub was describing. If you increase number of cavities, you increase, if you're talking about pi mode, you increase number of spokes. And if you have more spokes, ideally, you're going to have more power to extract. So you can enhance the power, right? Now, of this 12 cavities, they were able to extract more power, but the mode wasn't stable. It was jumping between pi mode to pi mode and something in between. So it wasn't so easy to control mode for this. This study was just done on CST, I mean magic, and you can notice that with the transparent cathode here. They tried to have 12 emitters, but still, like, there's a lot to do about this work, and they stopped because there's no fun to continue this type of work. Yeah, so again, some Chinese group, like, they're really big and good, and they have, you know, they have the resources to do experiments faster than others. And they came up with the rising sun that you saw this morning, and they open it axially. So they are trying to get like axial extraction diffraction output. And they usually like have a very nice results, but most of them are simulation. I don't know about experiment, how this is going to be possible. Could be, but their graphs, their, you know, FFT is so clean, you know, that I never done any source and we found this clean FFT. You know, usually there is more competition.
Why do you think so? I mean, what's the biggest problem in having an axial extraction?
Oh, okay. So one of them is like the electric current. The electron will leak from here. And how to stop them? You're gonna introduce maybe some end cap or stop, you know, this, and this is gonna affect your frequency, gonna affect your mode, right? Everything you add in. This is a conductive material, of course. You can't add any other dielectric. Yeah, these are some of the challenges. Rising sun has 2 cavities, so it's basically averaging over all of these frequencies, right? But yeah, it could be like there is nothing says this cannot be done. You know, you can be lucky and run the experiment and get like optimal results. Next day, you have a small misalignment because you have to have the cathode dead on axis. If you have like, and we do it by hand, there is nothing automated that you can give you like very nice alignment. You do it by hand, and then next day you're gonna have half a millimeter shift in one direction. Everything will, be different than the previous experiment. So this field is not, the good thing is the application doesn't require you to have a clean FFT. They require to have a lot of power to do the job. So it's okay if you have some mode mixing. This is another paper by I think this group in Texas Tech. I think they worked closely with UNM as well, so they were able to kind of replicate the Chinese paper on CST, but they never done any experiment. And they added this end cap as well, just to stop electrons from leaking. Now, since UNM came up with a different cathode structure, and they were,
What the efficiency reported?
At UNM or this one, yeah, you can, this is basically the efficiency with different orientation of the transparent cathode. This is degrees, beta degrees, which is the orientation of these emitters with respect to the cavities. Yeah, they play with that. And also, I think they play with the extraction angle, this one as well. This is theta, they call it. Yeah, so the efficiency reaching like 55 to 60%, which is very, very nice, At UNM, I think with the end caps, they reached 60 something, 62, I think, and then they end up with having window breakdown, and some electrons escaping, and they were challenging. And then Chris took the experiment and went to Air Force lab, and they continue with no publication, of course. So yeah, after like having transparent cathode, and they saw some improvement, AFRL started having what they call shaped cathode. So instead of having solid, they have like some different shapes to enhance, generation of the electrons instead of priming. And they got like some okay results too. Also, other group, Raytheon, K-Tech before, and UNM worked on what they call metamaterial type of cathode, which is rodded, like what you see here. And they were able to, to get good results with the iSpec simulation for that. Yeah, I don't have the results. I think I have a different presentation. If we have time, I can switch to that. But just to give you an idea how the rising sun is different than uniform cavities. Uniform cavities means all the cavities have the same dimension. Is that the dispersion curve? This is the mode number, or maybe the phase shift, or you can talk about like different, variations of its axis, depends on how you plot it. And this is the frequency. You notice that this is the rising sun, and the uniform cavities will, with the same number of cavities, of course, will have their pi mode here. So basically, you can have electron beam interacting with the lower frequency for the rising sun and higher frequency for pi mode for the case in uniform cavities. Okay, makes sense?
One more question.
Yeah.
The purpose of this selecting this rising star structure is just to more separation, or the other advantages?
Both separation one, I think. I think second, like it is easier to have a tunability, I think, and also, you know, switching from mode to mode easily, because you have two frequencies basically here. You can play with that. I never worked with anything with the rising sun, but it looks, you know, promising when I saw the Taxistic paper of this one. Yeah. Yeah, Chinese efficiency is 70%, which is very good. And they have, I think, transparent cathode too. So there is a family of these transparent cathodes. So they are not only one. And people like they try to come up with the different designs for that one. Last device I want to show you is the recirculating planar magnetron. Have you guys seen this before? I don't think anyone. This is from University of Michigan. They came up with this type of magnetron. It's like kind of a planar, and this is the inverted version. And the morning you saw inverted magnetron. Inverted means the cathode is in the outer, you know, electrode. So this recirculating planar magnetron gives like a bigger area of emission. So you can have more electrons, higher current, and then you can generate higher power. This is one of the advantages. Second advantage, I think there is another design. We did BWO. I will show you backward wave oscillator with the two slow wave structure to generate two frequencies. For some application, they need to have two frequencies in two different bands. So Taxistic, they have this type of two different cavities set. So here is like cavities, and here is like different size of cavities. And you have one electron beam, you can generate two separate frequency, dual band source. So that was another advantage of doing this. Nowadays, they are working on amplifier version of this. So as I was describing before, and this is afternoon, I will talk about O-type devices. O-type comes from a French word, but it doesn't mean much for you. It's basically just linear devices. M-type is having E cross B drift type of interaction. So the electrons drifting perpendicular to the applied magnetic field, static fields. O-type devices, electron drifting in the same direction, parallel to. So there is another crossed field device. This is called crossed field because they are perpendicular crossed. This is CFA, which is basically, if you take a look at the inverted magnetron, these are the cavities inside here. So you can do the same idea. The cavities here inside, and the cathode is outside here. And you can inject the RF amplified and then extract. This is called CFA. It's not well studied. Still nowadays, like they came up back to this problem because for higher, power, there is no, good work on, like people haven't done a lot of work and to investigate this type of devices. But this is now like, because the need for amplifier, high power amplifier is really critical and everyone want to do an amplifier. So CFA now back to, people like start doing more research on that device. Okay. So those all are slow wave devices because there is a slow wave structure, right? Sort of. And this sometimes is called Cherenkov radiation. It has, story behind it, but for any case, you can have some slow wave devices. It depends on where you are interacting between the electrons and electromagnetic wave. We will talk about dispersion curve. That's why dispersion curve is critical to understand dispersion curve. Dispersion curve, if you operate in the forward slope, positive slope, you have forward wave interaction, and this is one type of device. If you have a backward slope or negative slope, you're going to have backward wave type of device. if you are working in the almost zero group velocity, you have different type of devices. So you are changing the operating point, you change the instability, you change the physics of the device, and you're gonna have list of different type of devices. Surface wave oscillator, relativistic diffraction, diffraction generator, orotrons. You know, you can go ahead and read all of this. Fast wave devices are different behavior. So for slow wave devices, basically electron velocity is basically cannot reach speed of light. Always this is, remember this. So electromagnetic wave, to have a resonance, you need to have very close phase velocity to the electron velocity. So you need to slow it down, or you need to play another game. You let the phase velocity higher than speed of light as for bounded media, but you need to shift your electron dispersion curve somehow. And when we say shift, you can do it by having undulator, wiggler, like an free electron laser, or you have the cyclotron shift, basically, which is what I showed when we talked about cyclotron frequency. And this is gonna give you like a possibility to generate or to design gyrotron. And those are types of the fast wave device. And the gyrotron itself can be gyrotron BWO, backward wave oscillator, gyrotron, can be gyro traveling wave tube. So you can have different interaction, and then you're gonna end up with different device. I think this is the end of this. I'm not gonna be able to start talking about dispersion curve. So let's do it afternoon. Yeah, because it's gonna, you know, I'm gonna start with the kind of basic concepts, dispersion characteristic, and then move on to the magnetron and BWO. Any question about this part? I think there's a lot of overlap with this morning talk, but you know, you'll see things like with different perspective. It's very nice, you know. Thank you.
One question from me. What maximum RF power Ahmed achieved?
For relativistic levels, so it depends on your accelerator. If you have big Mark generator that can produce megavolts, you can have a couple of gigawatts, like maybe 10 gigawatts. So the efficiency, the key point for linear devices, BWO, efficiency around 25%. For BWO, more than 50%. Let's say 50%. So if you have 10 gigawatt input, you're gonna get 5 gigawatts RF. But 10 gigawatts Mark generator is really huge, so it's not practical. Yes. Oh, yeah.
What's the material of transparent cathode?
What?
Material for transparent cathode.
Graphite. We use graphite. We use tried stainless steel, non-magnetic. Works in the lab level, but graphite is the one that we chose. Yeah, all of them, they give good number of electrons. Yes.
Does not the number of electrons emitted by the cathode proportional to the cathode surface?
Yeah.
Why not the cathode surface corrugated? Is it like
Yeah, there is a couple of studies that is similar to the shaped cathode. So they have the corrugations and the
corrugation?
yeah. But still, like if you have a corrugation, you still have a conductive material. So your electric field, the radial component of the applied field, will not be maximum at the surface, because it's not going to go to zero on axis. It's going to go zero on the corrugation, right?
Corrugation.
Yeah. So you if you have like an opening in the middle of the cathode, you will enhance the electric field on the surface. So it's going to be higher, and it's going to give you, yeah, it's going to give you like faster electron generation. Yeah.
I have a basic question. If we compare with other magnets of this system reach higher temperatures, am I right?
Higher power. Yeah. So these are like low rate pulses. So pulse maybe 10 hertz, prep. So you don't have much energy. You are not suffering from like temperature. There is no much heat. You might need to cool it a little bit, but there is no heat problem because there is no average energy in this. So
There is no heated cathode.
yeah, there's no heated cathode. It's cold cathode. We call it plasma cathode. So yeah, power, peak power we are talking about. Sometimes it's confusing average power and peak power.
Okay, thank
Okay,
you, sir.
thank you.
As I follow on in the literature, these are very crucial advancements about magnetron technology. For this reason, I want to share my congratulate to the University of New Mexico because they have done very innovative and breakthrough advancements in this area. Thank you.
Thank you.
This informative
Thank you.
Now we will go to the lunch and we will continue at 2 p.m. Have a good lunch and see you.